In this video, we are going to look at examples of quadratic functions transformed, the transformations of A, B, and reflection. So in the first piece here, we can see a vertical stretch or compression based on if the numbers on the front of our function on the outside of the parentheses, and it's multiplication this time, not adding and subtracting, this will be a vertical stretch by a factor of 3 when this value is greater than 1. So anytime it's greater than 1, it's a vertical stretch of 3. This also makes your graph narrow. It's going to be stretching your graph vertically. So it's pulling. Think of a rubber band, pulling it and making it narrow. When you have a value on the outside and it's 1/3 multiplied to the entire function, it's going to be a vertical compression. This will make your graph wider. It will widen the graph from your parent function. When we're looking at horizontal stretch and compression, it's on the inside of the parentheses, and you're multiplying that value with x. So when you're multiplying with x, when it's on the inside, you have to think it's the opposite. Just like when we're talking about horizontal translations left and right, if it says +3, we're really moving left 3. If it says -3, you're really moving right 3. It's the opposite. So when you see a horizontal stretch by a factor of 3, you take the reciprocal of that. So 3, 1/3, the reciprocal you flip is going to be 3. Here, this will make your graph wider. When you have multiplication with a value greater than 1 here, then you're going to flip that factor, and that factor is going to be a horizontal compression by 1/3. So this will actually make your graph narrower. When you look at reflection about the x-axis, it will literally flip it over the x-axis, so it will go facing down, and so you're going to see the negative on the outside of the function. When it's reflection about the y-axis, it's a negative in front of the x, but this is tricky because your graph will stay exactly the same. So let's go ahead and look at a few examples of what that's going to look like. In example number 1, you're going to describe the transformation on f of x that results in g of x. So here, there's a negative on the outside. When there's a negative on the outside, we say that that is reflection across the x-axis. So we're going to fill out the table by multiplying all the y values from our parent function, f of x equals x squared, by multiplying the y values by -1. So that will become 4 times -1 is -4, 1 times -1, -1, and so forth. So what that looks like on your graph is your parent function will be facing up, and your reflection over the x will face down because it flips to the bottom. So then, describing the transformation would be reflection about the x-axis. Now let's go ahead and look at reflection about the y-axis. So this is a little bit different. You would think that it would change your graph, but when we look at an example of f of x equals x squared and g of x equals f of x with a negative in front of the x, this is going to be reflection about the y-axis. So give me 1 minute so I can move my... Okay. So this is going to change the x values because that negative is in front of your x values. The parent function stays the same. You multiply your x values by -1, and so now what you look at is this graph is exactly the same as the parent function. So the transformation doesn't really, you don't see a difference in the transformation when it's reflection about the y-axis. So it's just a note to yourself, when it's the y-axis reflection, it's not apparent on the graph because the line has, because y equals x squared, has a line of symmetry at x equals 0. So let's go ahead and move on to some more examples here. In the next example, we're going to be looking at a vertical stretch and compression. So this is where you see the value on the outside of the parentheses in front of the entire function being multiplied. So here, f of x equals x squared is your parent function, and g of x equals 2f of x is the new function. So if you're multiplying the entire function by 2, you're changing the y values here. So when I change the y values, I'm multiplying them by 2. The parent function stays the same. So my parent function, the new function will have your y values multiplied by 2. So what that looks like on your graph is it becomes narrower. As that value is greater than 1, 2, 3, 4, 5, it becomes narrower. So here, this would be a vertical stretch by a factor of 2. That number's on the outside is a true sign. It's a true number. In the next example, you have f of x equals x squared as your parent function. And this time, the new function is g of x equals 1/2 times the entire function, which is f of x. So if you're multiplying the entire function by 1/2, you're changing the y values and multiplying them by 1/2. So here, if I multiply all my y values by 1/2, the new graph will look like this. So here, your graph becomes wider as a is a value between 0 and 1. So 1/2, 1/3, 3/4, anything between 0 and 1 will make your graph wider. And so we call this a vertical compression by a factor of 1/2. It's compressing the graph instead of stretching it. It's compressing it, like making it flatter, so it's going to become wider. Let's go ahead and look at a few more examples. And let's identify, on these examples, we're going to identify and match the graph of g of x equals a times x squared. So this is on the outside, again, and this changes your graph to be wider or narrower, and it's the true value. So if I want to match the description down here with the graph above, I want to look at the graph and identify, is this graph narrow or is it wide? So when I look at this graph, it's narrow. So since this graph is narrow, I'm going to make a note to myself. This is narrow. That means A should be greater than 1. So my answer should be D. When I look at this graph, there's two things going on here. There's a reflection across the x-axis. So reflection across the x-axis. And this graph looks wider. So if there's reflection across the x and it's wider, we're going to describe this as a value between -1 and 0. So A is that number in front of the x squared. This graph here is wider. When your graph is wider, that value will be between 0 and 1, so C. And here on the last graph, this is also a reflection, and it's just narrower. So reflection across the x-axis, and it's narrow, so this is going to be B. A is less than -1. All right, let's go ahead and look at horizontal stretch and compression. When we're looking at horizontal stretch and compression, you want to recognize that this is on the inside of the parentheses, and it's the opposite, right? It's a reciprocal. So if we have f of x equals x squared and g of x equals f times and 2 times x, that's multiplication on the inside. This is either a horizontal stretch or a compression based on that description. So I want to recognize it's the opposite of what's on the inside. It's a reciprocal. So I'm going to be multiplying the x values by 1/2. So your parent functions is the same, f of x equals x squared, but now I'm going to multiply all the x values by 1/2. When I do that, the x values change. So my graph will go from my parent function, the purple, to the green. So this is actually wider. I'm sorry. Why did I say wider? It's narrow. From my purple graph, the parent function, to the green graph, it's narrower. And it's narrower because this value right here is greater than 1. So we would say that this is a horizontal compression by a factor of 1/2. In the next example, you have f of x equals x squared and g of x equals f times 1/2 x. So in this problem, again, you want to remember that it's the opposite of what's inside the parentheses. So you want to take the reciprocal of that. So the reciprocal of 1/2 would be 2. So here you're going to be multiplying the x values by 2. So in my table, you're going to notice that your parent function stays the same. Multiply all the x values by 2. So here in the graph, g is now wider. So this graph became wider when that value b is in between 0 and 1. So this would be a horizontal stretch by a factor of 2. Now you're going to go ahead and explore in your Desmos calculator, and if you have questions, please ask your teacher.